Mike, can you grab that remote control for that projector and pass it up here forward? Yeah, we got such an angle in there, I don't know if we can... Yeah, I think that's better.
There it goes.
Are we ready? Well, let's try her and we'll check it at the... Okay. This session of the Substation Design course is on two topics. First one will be outdoor substation structures. In the design of outdoor substations, there are certain factors that we have to at all times consider in evaluating different types of substations and different designs and the equipment that we use in the substations. First thing we have to consider is, of course, safety. And this can be made up of many different things that we have to consider in the design of the substation. First of several items that we want to consider is adequate clearances to live parts. This, I think, goes without saying that we want to have all the energized parts of the substation mounted at such an elevation that they would not provide a hazard to personnel or vehicles, whether intentional or unintentional. Second factor we want to consider is to make the circuit connections and substation design simple. Although this may mean that certain as far as maintenance and operating conditions, we won't have quite the flexibility that we desire because of the fact that we have a simple substation arrangement, the fact that the operator or whoever's in the substation can look at the bus conductors or line conductors and see just exactly where they are. It provides a reduction of the possibility of error in any kind of switching arrangement. We'd have to coordinate the installation of all the different pieces of equipment that we're going to mount in the substation and install in the substation. We have to establish a safe grounding procedure for the substation structure and all the equipment in it. We must have equipment located in the substation to reduce the possibility of a great extent of damage in case of a fire in one piece of equipment or an explosion in one piece of equipment. And finally, the substation structure must be lighted in some manner, provide adequate lighting so when the electrician or any person wanting to walk around inside the sub at night won't get into any danger from hitting his head or running into equipment. The next major factor we want to consider is the reliability and flexibility that we can build into a substation structure. The single line diagram of the individual substation is determined primarily by the size of the sub, the voltage levels involved, and in general the importance to the system. At the higher voltage levels, obviously we can justify a lot more money in equipment and substation design to increase our flexibility and reliability. We must be able to take the equipment and substation out of service for maintenance. Therefore, the structure has to be designed for moving circuit breakers, other equipment into the substation and out of it. We must consider possible airborne contaminations in the design of our insulation structure. The ease of expansion is a prime factor in many of the initial stages of a substation development, because quite often when a substation is initially installed, there may be a small load on it. This load could be transferred to other circuits quite easily. But 5 or 6 years later, the load on a given substation may be built to such an extent that it may be extremely difficult to get parts of the substation structure out to maintain the equipment or even expand the equipment. But in all of these, we pay a cost to provide increased flexibility in the substation structure, and will complicate, say, the metering and relaying in this particular substation. One example of this you might recall from the presentation on single line diagrams. A straight bus where you have a single current transformer or breaker provides, you might say, the utmost in simplicity, but yet it doesn't provide that same flexibility, because if you want to maintain that breaker, obviously you have to take the circuit out of service. In some of our larger subs, higher voltage subs, we go to a ring bus type system where you have 2 circuit breakers that are functioning for a single line. Therefore, if you want to maintain one, you can still have the second breaker closed and maintain service to that particular breaker. But this does mean more complicated relaying. You have to parallel the current transformer secondaries on the 2 breakers. So you don't get something for nothing, as the saying goes. Third factor we have to consider in a specific substation is the development on a particular site. We have to consider the land available, how much we have, and what its cost is. We have to consider the direction that the lines are going to come into this substation, whether we can come in from both ends, from all 4 directions of the compass, or whether they're going to be restricted to a certain area. And a factor that's more and more prominent the last few years is the substation structure should be simple and pleasing in appearance. Components of an outdoor substation are listed in the first part of our outline. There's basically 5 sections that we want to discuss. First, the supporting structure, the insulators, the bus conductor, the connectors, and the disconnect switches. Early subs in the history of the electric utility industries were indoors, because at that stage of the game the equipment had not been sufficiently developed that they could operate this stuff outside with all the possible damage from weather, from lightning, from rain, which would destroy the equipment. We have several continuing examples of this here in the Quad Cities. All of our older 13 kV subs initially had indoor open bus work. Sub-R, Sub-T, Moline Plant, all of these were initially designed and operated with indoor buses. At our present practice, we have an outdoor structure in all of our 69 kV, 69,000 volt subs and above. In some of our rural areas, we have a 13 kV outdoor structure, that is open structure. 13 kV and below, in our company, we go to metal-clad switchgear. Just to give you the idea of the relative cost of these different components of a outdoor substation, there's a very good summary in the one of your references there, paper 62-246, which for a 161 kV 4-circuit ring bus, the 4 different components that we were talking about and listed in your outline there, we can give you kind of a cost breakdown as to what each one would be as a percentage of the total substation structure cost, not equipment cost. But the structure itself would be about 28% of the cost. The insulators, 5%. The bus, we mean the bus conductor, about 3%. The connectors on the bus and the equipment, 2%. And finally, the disconnect switches, 62%. So you can see that the major cost item in any outdoor substation is the disconnect switches. This percentage will change approximately with different voltage levels and with different configurations, but it's still going to be in the range from 60 to 80% of the total cost of a given outdoor substation. So now we want to look at these 5 items one at a time. All our outdoor substation structures, except 2, are galvanized steel. The 2 exceptions being the structure at Sub Q in Bettendorf and the Nightman subs, which are made out of aluminum. Aluminum is used in areas that are contaminated from industrial contamination, or in areas that we anticipate a contamination problem. In the other areas where the galvanized steel structure is, in general, less expensive and performs quite satisfactorily as far as strength. The different types of structures or functions that are performed by the structure. First, we must have a means of dead-ending the incoming lines coming into this structure. So we have a dead end for the line structure. We must have a means of supporting the disconnect switches that we mentioned previously. Depending upon the particular bus layout arrangement, we have to, in certain cases, have a pedestal type of support for the bus, or we have to have trusses at the end of given bays to support the strain bus. So we have to have a bus support type of structure. We have to have mounting for the lightning arresters and potential transformers that are a necessary part of any substation. And finally, we must have means of shielding or protecting this particular substation from a lightning stroke, either by a separate mast or by wires strung from portions of the 69 kV or portions of the substation structure. In designing this, we have certain strength requirements based on whether the line coming in is going to be take the full strength of the line, as are we going to come in from, say, a tangent pole maybe 150, 250 feet away, or whether we're going to have a pole that'll take the full strain of the incoming conductors right outside the substation structure, and all we're talking about is a short span of relatively low tension. So we have to consider that. We have to consider the physical weight of all the equipment that would be mounted in the structure. We have to consider the different wind and ice loads that might be presented at different times of the year. The electrical clearances that we are going to be using, and I want to point those out in the second sheet that you had over there, are the ones that have been adopted as standard throughout the country as a guide for the minimum requirements. I want to emphasize that's the minimum requirement. In a specific substation or a specific company may want to increase these figures right here, but if you were to use these in your substation design, you would have achieved the goal of the electrical clearances that would be necessary to maintain the BIL, or the basic insulation level, for that particular voltage. Might go over those briefly. I've listed them for 3 voltages that we are using in the majority of our work: 15 kV, 69 kV, and 161 kV. At some of the higher voltages, 345, we haven't gotten the degree of standardization in the industry yet, But at these voltage levels, these figures are accepted as standard for the minimum electrical clearances. And I think most of them are self-explanatory. The BIL level, the minimum clearance to ground for rigid parts. Well, I mentioned this is rigid parts, and therefore if you have a strain bus, you'd have to take that into consideration, something that's going to be moving. Minimum clearance between phases or live parts for rigid parts, metal to metal in inches. For instance, if you're laying out 2 phases or 3 phases where you have a bus support with a conductor size or the top of the insulator cap of a certain diameter, you'd have to take that into consideration in determining the minimum clearances. That is, this is the minimum metal-to-metal clearance between parts, not centerline of phases. Minimum clearance between overhead conductors and grade for personnel safety inside the substation in feet. This is, as you can see, this would in general allow a person to walk around inside the substation and still maintain the minimum clearance to ground that's listed in the second column above that, the second level above that. Minimum clearance between wires and roadways inside substation enclosure in feet. These give the consideration of somebody, for instance, a person riding around in a truck, in the bed of a truck, a man standing up there holding his hands up in the air. You still would have adequate clearance to any kind of energized conductor if you were driving around in that location. That was the basis for these figures here. There are several general types of substation structures that have been used and which we use quite a bit in our outdoor substations at 15 kV and 69 kV. The common type of structure has been what's called a continuous frame with an individual beam. In this case, we're talking about a substation structure that has definite bays, but the columns are single beams. This would be some type of wide flange beam or column beam here, and the cross members would be that same type of construction. And then we'd have others coming up here, and looking at it in a perspective, this would continue on down this direction. We'd have another bay down here, and that would be laced across to this bay here, and then continuing on that way. This would be the type of structure that's quite common in our 69 kV substations up until the past few years, this continuous beam. Now we have one example of this continuous type of substation structure, the laced framework. And we have this same general arrangement, but each of the columns is composed of an angle and with a lacing back and forth, something like that. Substation 58 in Bettendorf has this arrangement, and it does present a little more bulkier appearance. Now, at the 161 kV levels and above, we're kind of forced to go into this type of a structure because we're talking about separate structures. At the higher voltage levels, we don't have any continuous structure. We have separate structures for line dead ending, separate structures for disconnect switch mounting. So it's more economical of steel to go to a laced type construction like this. A type of substation that you hear mentioned quite a few times recently is called a low-profile sub, of which we have 4 or 5 examples here in the Quad Cities. And kind of the distinguishing factors on that is the fact that we're talking about structures made out of beams, first of all, then they're, in general, lower to the ground than the open-type continuous frame structures that we had been talking about. And we'll see some examples of these a little bit later. But we make every effort to keep design our structures so if they're low to the ground, if we have disconnect switches, we have them mounted on a pedestal type support like that. We use tubing buses, which we'll mention a little bit, to keep the overall level low. But this is what's talked of, or what's meant by a low profile type of substation. The substation structure as we received it, of course, is just a pile of beams and angles that you have to assemble. First part that is normally received within 6 to 8 weeks after ordering the structure is the anchor bolts, which we use to tie the exterior structure to the foundation. The structure can be assembled partially on the ground. Usually we use different means to make sure that the bolts we use to assemble these structures won't come off. For quite a period in our early history, we punched the threads on these bolts. That is, after the structure was assembled, it'd be up to one of the electricians or linemen to climb over all this structure and use a center punch and punch the threads of the individual bolts so that there wouldn't be any possibility of the nuts vibrating loose. The next development that we've used have been pal nuts, which is a type of lock nut that's screwed on after the structure is assembled and tightened. We're specifying this on all of our 69 kV and 161 kV structures. There are other different type of lock nuts, but we haven't used them extensively as yet. You'll note in all of our structures that have any height on at least one column or one side, we have step bolts to allow an individual to climb up to a higher level. Each leg of, or one leg of a separate structure and each leg of a continuous structure provides means for connecting a ground wire from the structure to the substation grounding grid. Now let's take a look at some of these different types of substation. This structure here is what's called the continuous frame structure made out of beams. As you can see, we have a line coming in here, dead ending on this truss right here. This would be the insulators. From the incoming line, we step down to a bus conductor that's supported by these bus supports right here. Goes over to this disconnect switch, comes down through the circuit breaker, up through another disconnect switch, and then is connected to a bus support here. And in turn, we tap off at this point through a fuse to a potential transformer. At this point, we tap up to a bus that's running in and out of the paper here. But each of the structure members are made up of a single beam at various points. You can see in the background we have cross bracing of steel angles to maintain the structure vertical during extreme wind and tension loads. The design of the steel structure is quite critical in that we have to keep the structure rigid, make sure we don't get any problems in operating the disconnect switches here. If we're out of alignment a little bit, why some of the different switch parts might bind and make it hard to operate. Like I mentioned previously, if we have any questions, well, I don't hesitate to raise them as we go on here. This structure here is an example of a laced separate structure that's used on 161,000 volts. As you can see, comparing some of the dimensions here, we're talking about much bigger structures, even though they're, according to the drawing, they're about the same size. But you can see in our 69 kV structure, we're up at about 36 feet to the bus here. Here we're up 40 feet. We have 14 feet between the shield wire coming in here and our phase conductors. This structure right here, which is the dead end structure, we'll see some pictures of it a little bit later, is made up of heavy angles, about 5 by 5 or 6 by 6 angles on either side, with a lacing back and forth here. This is a truss here that's laced, and this particular case we come in from the line with a conductor here that's supported by these two bus supports, and then we hit this disconnect switch here. This switch stand here is a separate stand made out of laced construction, and in this case the bus is a strain bus, so we go from this disconnect switch to another disconnect switch here that's used to support the breaker isolating disconnect switch. This would be a 161 kV breaker. And as you can see in this particular sub, we have an overhead shield wire. This would be the line shield wire coming in. It extends from this structure to another structure here and goes through the structure and then continues on all around the structure so that it provides a shielding cone over all the bus in the substation, all the equipment that would have a possibility of being damaged by a lightning stroke.
Question.
Yes.
On that shielding wire cable, you have what, 7,700 pounds per W?
Yes.
What does that mean?
Per wire?
Per wire. Okay.
Yes. And
So
here's 11,200 pounds per wire, so then we'd have 3 phase wires,
I see.
each having 11,200 pounds, and at the top we'd have 2 shield wires, each 7,700 pounds per wire. So you can see this is going to be a pretty hefty moment here and pretty hefty structure. And that's one reason for this type of structure with a widespread base here, provide a greater base to resist this moment. There's quite an overturning moment that is, this structure here would tend to pull this back leg out of the ground. So this is also quite a critical factor in foundation design. You have a uplift or a force tending to pull the foundation out of the ground. This structure here is what we call a low profile structure. And the structure is made out of more of a single beam, where we have incoming line here. We go down to a tubing type bus here, and the disconnect switches are supported on single structures. In this particular sub, we have a height of about 15 feet to the bus. As you can see from your table there, we're exceeding the minimum values quite a bit in 69 kV, and we're considering going to a lower level in some of our newer 69 kV subs. Some of the other components of the 69 kV or any kind of a substation design, I think we've discussed in previous sessions. The insulators, the bus support insulators, the strain insulators would be involved in many of the same factors we discussed during the insulator session. The insulators would have to withstand the normal voltages, the same impulse and switching surge voltages that we had previously discussed. One fact that we had mentioned is that in certain areas we may have to take into account the possibility of atmospheric contamination. Some of the places in the Quad Cities, for instance, that we have considered this, at Riverside. In fact, all of our 69 kV substations have taken into account the fact that we have the possibility, being an industrial area, of airborne contamination. Our basic 69 kV insulator is a non-standard insulator. It has a higher creepage distance, that is a greater height, more surface for airborne dust to accumulate on before there would be a possibility of a flashover than the normal 69 kV insulator. At Riverside, for instance, where we have an extreme contamination problem, we went to quite an extent. In fact, we built a barn over part of our 69 kV substation structure there because it was directly in the path of fly ash from the Riverside stack under certain atmospheric conditions. And we had some extreme conditions there. Keith can vouch for that during the early 50s, and we had a very engineering, very logical type consideration there. That is, our president said, just put a barn over that. So that was the way we decided to do that. Question, John?
Why has some of it got the barn over and some of it hasn't?
Well, that was the basic thing is that's right. We have a new president.
If you built the bus, he didn't want a new barn.
Well, we haven't had the same public relations considerations since then as we had in the early 50s. Plus, I think we are not exactly in the right areas. We're trying to build some of the other subs a little farther away from the stacks there.
Right, Riverside. Right beside the barn, there's another section of the sub.
Yeah, to the upstream side.
I think we embarked also on insulating washings at the same time. Where do you still have problems out there?
Yeah, it isn't a complete answer, but we don't have to build any more barns. That's the only thing. And we do have our standard 69 kV insulator, which was picked primarily on the contamination problem at Riverside. Has a greater creepage distance. It's higher than the standard insulator. Some of the other, for instance, the R5 69 kV leads are greatly over-insulated as far as suspension insulators. We use 8 suspension insulators per string instead of a normal 6. But as Jack mentioned, some of the others, we still have problems out there. It isn't a complete answer. Maybe question?
You were mentioning structures. You got one wooden structure out at Bluegrass.
Yeah, we still have those. I didn't want to mention those, so. Yeah, I think Bluegrass, and at one time we had several metering structures that were made out of wood. And in fact, in some of our other districts, at Barnum and in the Fort Dodge area, I believe we have a wooden type structure also. But we're trying to overlook those. The mechanical forces on the bus support insulators would come from 2 areas. First, the normal weight of any equipment they're going to support, and second, we have to consider the fact that in any kind of a structure, when we have a fault current, we're going to have a magnetic force that's going to be tending to either pull the 2 phases of the circuit together in case of a phase-to-phase or 3-phase fault, or push them apart. So you have a fault current generated force there that you have to consider in the bus design. This means, for instance, out of Riverside, that our 69 kV bus there is good for 3,500 MVA. This means that when we have fault currents that are going to be exceeding 3,500 MVA, we're going to have to consider rebuilding our bus out there or making certain other operating changes to limit the possible fault to 3,500 MVA. The type of insulators we use would depend on the type of structure. In the continuous frame type of substation, we use the regular bus support insulator, either cap and pin or the post type, for the insulation and the disconnect switches and other buses. We also use a suspension type of insulator for the strain buses. Our bus conductors, I think we mentioned in previous sessions to some extent also, the current requirements would depend there again on the voltage level, on the type of sub we're talking about. But it should be a current rating that would not limit circuit breakers or disconnect switches. We usually use the current rating at the 70-degree centigrade copper temperature. As far as mechanical strength, strain buses in general are strung at fairly low tensions in substation structures, and there are no specific mechanical strength problems there in most cases. The tubing buses, the size of the tubing is primarily concerned by the span length that we want to bridge instead of the current carrying capacity. That is, for each type of conductor we have a certain span that we can go between bus supports without developing unusual deflections there. There are several types of conductors. We mentioned cable and tubing. It can be of copper and aluminum. And we also have some special shapes that in certain cases have been used as bus conductors. I don't know that we have any specific examples, but in some cases we have aluminum angles. Aluminum being a conductor we could use as a bus conductor. And at the higher, extremely high current levels, say in the 4, 5, and 6,000 amps, we quite often use a channel bus, which these would be channels made out of aluminum or copper, because we get better strength, better current carrying capacity on those special bus shapes. John?
Is there any voltage limitation on channel bus? Like when you used to make it 345? Would we?
Well, I'm sure there would be because of the corona levels.
Yeah, that's what I was thinking.
I'm not familiar with any, or I've not seen any pictures of 345 kV subs that they use anything other than tubing, primarily from the corona standpoint.
With all those wheels are distributed.
Yes. We got a note here that the car lights are on Illinois license FY7864. I don't know if that's anybody's car here. It's a yellow Chevy. Well, lights are on in case anybody wants to go out and turn them off. The type of connectors we use in substation, even though they're a small percentage of the overall substation investment, quite often get into quite a few problems because of the vast diversity and connections that are required. Functionally, we can have we have different types of connections. First one might be a straight connection. I'm going to use tubing examples here just for ease in picturing them. But if we have two pieces of tubing here and we want to connect them, we'd have a straight connector there. And another type would be a T-tap, whether we want to tap this tubing and bring another piece of tubing or conductor off like that. If this tubing were to extend onto a disconnect switch, it has a pad here, and so we'd have to have a connector here that would bolt to the pad and at the same time bolt to the end of the tubing. All this bus would be supported by bus supports, and we have to have a connector here to fasten the tubing to the top of the insulator. It's called a bus support connector. In all our suspension bus, we have special connectors for a strain connection and a suspension clamp. The majority of the connectors we use in our substation are bolted connectors. That is either copper or aluminum body with several bolts that connect the two pieces together, or the different pieces together in a given type of connector. At our 345 kV subs, we used welded connectors, welded aluminum connectors. And these become quite economical when you have an extremely large number of connections to be made, and they're of a large tubing diameter that would be very expensive using a bolted connector. It does require some skill in welding aluminum, which prevents it from being used extensively unless you do have a substation, as for instance a 345 sub, where you have an extremely large number of these connections. We need flexible connectors to connect the tubing, primarily to connect tubing to equipment, to allow for expansion of the tubing under high ambient and current carrying conditions. If we use a stranded copper or aluminum connector, inherently we have a flexible connector, so we don't have to consider that. We have a problem on copper and aluminum connections. They have a particular type of corrosion called galvanic corrosion, and they have a given series of metals in which, due to the molecular structure and the chemistry of the metals, metal will leave one particular individual metal molecules will leave one particular piece of metal and are attracted to another metal in this same series. Aluminum is a anodic type of material to practically every other material. This means that particles of aluminum will leave the aluminum and transverse to the other metal if you have the right conditions. So in any copper to aluminum connections, why the factor that you have to consider is to eliminate these conditions that would tend to cause the corrosion. And some of the things we do this, first of all, the aluminum should be installed above the copper conductor. This would mean that any rain or moisture that would tend to flow from the aluminum to the copper. And this would be in the direction we want, because the copper salts would corrode the aluminum, and it doesn't work the other way around. So we want to try, if all possible, to mount the aluminum conductor above the copper. Second thing we do is to use a particularly or specially designed aluminum conductor that is heavier, it's more massive, it contains more material than a similar copper conductor. This means, first of all, there's more material to corrode. You don't have a strength problem there, and it reduces the stress or the electric current over the given area of the connector. In making any kind of aluminum connection, we use a compound that protects the joint from atmosphere, and then the usual procedure is to scratch through this compound, through this grease, so that you eliminate the exterior surface of the aluminum conductor. This disturbs or opens up the bare aluminum and allows you to get a much closer and much tighter connection there. Now let's take a look at some of the different types of connectors that are available. These are a series of catalog sheets that show some of the connectors that are used. We don't use all of them, but some of the factors that you have to consider. All these are bolted connectors. You can see these are tubing to tubing connectors. Different types of T connectors there, where this would be your run, the tubing going in a straight line, you're tapping off. These would be straight connectors, joints. Here you're going from one size of tubing to another one. There's a X tap, T tap right there, T tap with two taps coming off. And then in the cable to cable section, we'd have about the same range there, different conductor arrangements. These are what's called a parallel groove type of clamp, which the two conductors are side by side. Here's some more different types of connectors. There's tubing. We have a tubing run and a cable tap. Different uses of copper bars, square tubing, which in some cases used as a connector. These are some examples of flexible connectors that are used. You can see here we have a switch terminal here that were bolted there, and these are thin sheets that allow this particular conductor here to move in and out, expand. Same thing right here. This is a tubing connector in which this part of the clamp is bolted to the tubing, and this part is bolted to the switch terminal. And this guide here allows this section of tubing to move in and out. These are connectors specifically for grounding substation. This one would be for grounding a steel column, for instance. You'd has a single bolt that you'd bolt to a hole in the structure. And some more connectors. These are what are called stud connectors, where we're coming from a piece of tubing or cable and terminating on a threaded bushing in a circuit breaker or a transformer. And these are terminal lugs for terminating on a disconnect switch. And you can see there's an extreme variety that is available. Most expensive part of the substation structures we mentioned were the disconnect switches. And they're classified in many ways. We want to go over briefly some of these classifications. This is a section from the standards on the disconnect switches, giving the different voltages and BILs and the different current ratings, continuous current ratings, and momentary current ratings are available in the different switch types. These single brief diagrams illustrate the different types of switch constructions, in which the triangles represent a bus support insulator. This switch here, the vertical break disconnect switch, is, you might say, the common or standard disconnect switch used in our substations. It's called vertical break because the blade, this part here, moves in a plane that is perpendicular to the base. It opens up this way. A double break switch, which we'll see better later, has a center rotating insulator and breaks at two different points. Tilting insulator, which we may have a few, but very few. This insulator stack here is hinged at this point, and to open the switch, why, this stack here is turned and it draws this part of the blade out of that contact. Side break switch, which has a rotating insulator here and a contact here. Center break switch, two insulator, in which the two halves of the blade meet at the center. Each insulator rotates. Another type of tilting insulator. And then a grounding switch, which I don't have an example. We have very few on our system. About the only place I know we have any extensive amount is out at Hills. But it's a switch that's used to provide a direct ground on any kind of a transmission line. It's primarily used as a safety means to allow easy grounding of a transmission line. This is a type that's kind of gone out of vogue in recent years. And this is a hook stick switch in which we have a blade here. It's hinged at this point, and a lineman or a substation electrician can physically pull this hook, this eye here, open to open up the circuit. Now I want to go into the first type of insulator, this outdoor vertical break. And this is this example here happens to be a switch that's manufactured by ITE TTR49. It might be considered our standard outdoor vertical break disconnect switch, the one we have had the most experience and the best experience with. It seems to work the best. This says a vertical break. The blade moves in a 90-degree fashion here. We have insulator stacks, 3 insulator stacks here. The rear stack here swivels, turns, and in doing so it pulls the blade open. We have a jaw here, and part of the jaw determines whether the momentary rating of this given disconnect switch, depending on these little fingers that you see here. You have a single one is 20,002, 40,003, 61,000 amp momentary rating. This means it could withstand the forces that would be produced by a fault of that rating. And also the temperature increase that would be produced by a current of that rating for 4 seconds. At this point, you can see by the dotted line, there's a provision that I want to put what's called an arcing horn. It's a means of providing two pieces of the switch here, so that if any arc would be present, the arc would be broken on the arcing horns, and therefore the main contacts would be protected from any burning. As you can see, it can be mounted in several different positions. This is called upright position here, which is used quite often. Vertical position here, where it's mounted on a truss, and the underslung position here, which is not used very often, which the switch opens downward. This is might be our standard 69 kV switch. The insulator used is as a 3-inch bolt circle. Guess that would about cover that. Next one we want to look at is the center break switch, in which the center insulator stack here rotates, and as you see, it turns in this direction here and provides a break here and here. Tilting insulator is kind of an interesting type of switch, but we don't have any. I can't really see the advantage of it, but some companies use them. They have this particular one, we have a 3 insulator and a 2 insulator center break switch, in which we have a movement here. There's a rod that goes between the phases here and pulls this blade open. And the same thing over here. The rod moves this insulator to this position here to open the switch. It's called a tilting insulator switch. This is a single break, also called a side break, which we have one rotating insulator. We open the contact at this point right here. This type of switch here is a center break switch, and it's used fairly extensively as a 69 kV switch on transmission lines, where it's mounted on poles. Both the insulators rotate here, and we have a point about in the center that breaks the current, or opens the circuit rather. Here's an example of a hook stick switch, which this is mounted on a set of cross arms on a pole, for instance, and we'll see an example of this later. And we have two insulators here, and the lineman physically climbs up so he's close enough so he can use a hook stick to hook the end of it in this eye here and pull it open to this position here. This is kind of a curiosity. We don't have any, but it's called a pantograph type of switch, used at EHV levels, in which the bus conductor is at a higher level here, and the switch here just telescopes like a pair of ice tongs in the open position. So to close it, while you in effect close the ice tongs, and these contacts here move up and clamp on the bus conductor on the overhead bus. It has some advantages in EHV type of structures. I think we've gone over most of the parts of the switch during this discussion here. We might mention briefly the types of operating mechanisms for these disconnect switches that are available. This example here shows the switch mounted on a wood pole, but the switch handle here, which is a pipe type handle, actually operates the center insulator, and then through rods, the center insulator translates or moves this motion to the two outside insulator stacks. This type of insulator here we have in a structure where we have a bearing here and then a kind of a pump type handle here, that's pulled down to open the switch. In our substation structures, we purchase everything that I've shown you and I have mentioned in the Roman numeral 1, components of the outdoor substation, from a single supplier. Not that this particular supplier would handle all these parts, but it reduces our engineering time, because we can write a single spec and let the supplier then take care of buying the insulator, the bus, the different connectors that might be a part of this substation. On extremely large projects, or those handled by our consulting engineers, we can buy the individual parts specifically from the manufacturer. That is, we buy the insulators from an insulator manufacturer, the steel from a steel fabricator, the bus conductor from the cable or tubing manufacturer. Just some idea of the range of a cost of the substation equipment. 69 kV low profile substation with provisions for 2 69 kV lines and a transformer have been running in the order of $25,000 to $30,000. As we get into the higher voltage levels, we don't have any meaningful cost figures, because it varies so much with the amount of steel that you purchase at one time. I want to mention these references that we have here. All the AIEE papers that are listed here are in our electric engineering department library, and some of those are fairly complete for comparing and explaining the different types of substation designs. Do you have any questions? Well, let's take a break and be back at 6:30. See, how's the focus on that? Is that okay? Looks like it's okay from here, but I can't. You may get zoomed in on once in a while, Keith. What we want to go through is some examples of substation structure and equipment in substation structure. This is a 161 kV lace type structure. We can see the lacing here, the line coming in here, the insulators, and then dropping down from this tap right here. This would be a T-tap. This happens to be a bundle conductor bus, so these are spacers, and this would be a disconnect switch here. This is a 161 kV ITE type TTR49 disconnect switch. We have the connector here and a 90-degree connector there. That shows some of the variety of connectors that we have to use. And
Question, Gordon.
Yes.
Looks like a big battery up there.
this is a piece of equipment that Charlie Luther is going to talk about. It's called a line trap.
Oh.
Basically, in all our 161 kV circuits, we use power line carrier to transmit at least relaying intelligence from one end to another. And this piece of equipment here prevents those signals from going back into the substation bus and going places where it shouldn't. And this is another example of closer example of the disconnect switch structure, a lace type structure here. 161 kV, we use 4 pin type insulators. You can just barely see this bundle conductor bus composed of 2 500 MCM conductors with a spacer there. This would be a stud connector there. And I don't know if you can see it, but right along this column here, it looks like there's some step bolts installed so that somebody can climb that column if they had a reason to. Let's see. I guess we don't, yeah, you can just barely see the shielding conductor coming in there and going out there. Somebody have a question? This is another picture in a 161 kV sub showing the lace type of structure. This is some of the smaller structures for mounting equipment. Just stands here, the mounting coupling capacitors and lightning arrestors there. Now this is a 69 kV continuous beam type of structure. Here's the columns that I mentioned here, the beams coming across here. They have cross bracing, angle cross bracing, a line coming in, and dropping down to the disconnect switch there and going into the circuit breaker, coming out through another type of disconnect switch, and then to this tubing cross bus here. You can see we have aluminum tubing, T connectors there, bus supports there. It's a shielding mast at the top of the structure and the shielding lines coming in there. And this shows some of the structures for mounting equipment. These happen to be three-phase structures, so you can mount 3 lightning arresters there at the same time. You can see here the provisions for grounding each structure. This happens to be an example of our low-profile substation. This is sub 36 over in 7th Street and 30th Avenue in Rock Island, Moline, in which you have the beam here, line coming in, dead ending there. We're using gray type insulators. The disconnect switch here. Yeah, shield wire coming in there. And this is another example farther back into the substation. This would be a bus support type of structure, which they have primarily to support this. These bus support insulators here support the structure there. There's a good example of a bus support connector. It's the T-tap, where we're tapping a tubing bus with a aluminum connector going down to the potential transformers. There's a good example of an expansion connector. Here you can see the disconnect switch, the 3 fingers there for a 61,000 momentary rating on the 1200 amp switch there. And these are the shielding masts. Those 3 wires come and terminate on these 3 structures here to shield the 69 kV sub. This is another sub. This is sub 27 in Green Rock, having a little different type of entrance. They're just a single continuous beam there. And this is another example of sub 27. Line trap here, shielding masts here. In this case, we don't use a shielding wire. We just have the tall poles sufficient enough to provide a 45-degree cone of protection over all the equipment. This is a little closer view of